Hi everybody, this video is for Friday, November 7th. What we're going to do is go over some cost estimation models today, talking about the unit method, which was first introduced in class on Wednesday, but we'll go through the in-class exercise for that, which I previously talked about and distributed. We're also going to discuss how a cost index can be used to account for changes in price over time. And then also the learning curve approach, which takes into account improvements in efficiency over time. So just a couple of reminders before we get into that. Your next homework assignment, homework number 12, that's posted on Blackboard right now, and it's due on Wednesday, November 12th. And then the project will be due the following week on Wednesday, November 19th.
Okay, so this first problem is saying you're going to manufacture 1,500 sections of gas pipeline, and we know how much steel costs, what's the machinery cost, labor, and indirect cost. So try and put together a cost estimate to manufacture these 1,500 sections of a gas pipeline. It's just kind of like a standard algebra-based word problem here that's giving you a taste of the unit method. Okay, so if we use the unit method to find out how much this gas pipeline is going to cost, then it looks like the steel is $137,000. The machine and tooling, $180,000. The labor for the casting and treating is $165,000, $54,000 for the finishing and shipping, and then of course we have to cover the indirect costs of $30,000, and so the total cost here would be $566,700. A cost index is a ratio that helps you to understand how costs in the past can be used as a data source when you're preparing for a future project. So for instance, there is a construction cost index that shows the cost of single-family homes over time. And what they did is they picked a certain year and they said, let's make this the baseline benchmark year. So it looks like here it's 2005. I know this is hard to see, but let me zoom in a little bit. So if 2005 is the benchline year for how much it costs to build a single family home, what they're saying is in 1964 it cost 12.4% of the cost in 2005. And beyond 2005 you can see the effect of prices going down a little bit after the big economic crisis that happened due to the housing bubble, but then they kind of have skyrocketed in more recent years. So now, compared to 2005, it's 186% more expensive than it was there. So, like if you had data, like if in 2005 your parents built a house and their house cost $200,000 to make, so if you know that in 2005 it was $200,000 to build a house, that same house today in, let's say, at the end of 2023, was 186.3 divided by 100. So this ratio is the cost index. And so the $200,000 was the cost in 2005. The index in 2005 was 100. The index now is 186. And so then you could find out what's the cost today by multiplying the past cost by the ratio of the index values. So that's just an illustration. There are lots of different data sources related to how prices change over time. The CPI is the Consumer Price Index, and it shows the cost of the types of goods that you likely consume on a regular basis. So it includes things like food, energy, vehicles, medical care, shelter, transportation. And so this is showing how prices have changed over time, how there were big spikes, for example, in the cost of fuel oil through the last couple of years, but then certain things have become a lot less expensive, like there was a big run-up in the cost of used cars for a few years. You probably remember that, when used cars were really expensive, and now they're relatively cheaper than they were in the past. So the federal government keeps track of the cost of items over time. And it's interesting to look at what they assume you're going to be consuming and the types of data they gather. So they gather data on food as a broad category. They think that the average American spends 13% of their budget on food. But then they even break that down into food that you'd consume at home and food that you eat outside of the home, like at restaurants and convenience stores and so on. And then they look at the change in prices year by year, within a month. So they're looking really at a lot of detail. And if you look at how many different subcategories there are here, so food at home, one of the subcategories is cereal and bakery products. Subcategory there, flour, breakfast cereal, rice and pasta. Even within bread, they break it down into white bread and bread other than white. So it's really a lot of resolution. Somebody's gone to great lengths to gather all of this data across the country. They have people whose job it is to go into grocery stores and other establishments that sell food and household items and clothing and looking at the cost of fuel. They gather all of that data, and on a month-by-month basis, they're looking at how it changes. And this sort of data is very useful to banks and companies to know how they should adjust their prices due to demand. And it can also help us from the perspective of cost estimation to know how to predict the cost of something before it's built. Whether we're preparing an estimate because we're going to buy or build something, or if we're a company that is going to be doing the construction or production. So this is the generalized formula for what I just showed you on the whiteboard a few minutes ago, that if you know the cost at some past time, C0, you can multiply that by the ratio of the index values and predict what the cost is going to be at some present time or time in the future if you have a predicted index for that future time. So this is the problem that we didn't get to in the in-class exercise from last time. And so because we're pressed for time today, I want to make sure that we get through the learning curve part of it. I'm just going to show you the solution to this one and give you a time to copy that down and hopefully see if it makes sense. So let's talk through it together, and then I'll show you the solution to this one. Basically what it's saying is that we had a repair garage in 2014 constructed, and it was $650,000. And we knew that there were 3 different categories of things that went into building that garage. There was the labor costs, the materials costs, and then the cost of operating and maintaining the equipment that was used in construction. And we know the index for each of those back in 2014, and then we know what the index is in, I think yours says 2024. I updated the handout, haven't updated the screen. But we want to know basically how much is each category going to be, and then how much is the predicted cost if we're going to build the similar thing again in the future. So for this one, part A is saying to calculate the weighted index. So to get the weighted index, we have to multiply the percentage of the cost for each category by the index value for that category. So you can see equipment is 50% of the cost, and so its cost index is going to be more important than the index of other categories because it represents a greater share of the overall cost. So the weighted index, when we take these percentages into account, is 149. And if we assume that the same weights are going to exist in 2024, then the updated index would be 178.5. So that's the updated index for 2024. So if you want to predict what's going to be the future cost of the garage to construct, the future cost of the garage would be the past cost of $650,000 multiplied by the ratio of the index values. So the ratio of 178, which is the current year's index. 149 was the index back when the item was originally constructed and built for $650,000. So that means that the predicted cost for this future similar structure to be built is $778,691. And then what we could do from there is break it into its subcategory costs. And so the subcategory costs of labor, material, and equipment, you just multiply the 30% for the labor, 30% of the whole value, 20% for materials, 50% for equipment, and we find the constituent costs as well. So I apologize that this is saying 2008. Here where it says 2008, I think on your handout it was saying 2024. I need to update the solution for that. But all the other calculations themselves are accurate. The index values, the percentages, and the costs are all accurately reflected. So I'll give you a moment to write that down. So the assignment that's on Blackboard right now includes some calculations very similar to this, where you are given index data for a certain year, you're given the price in that original year, and what it's asking you to do is basically use an extrapolation or a linear interpolation, you can think of it as, to predict what the future cost may be based on the old data. Now remember from the discussion that we had on Wednesday, this only works if the thing that you have cost data for was in a similar environment to where you're going to be building the new thing. So in the case of this repair garage, if the old repair garage was built on like a rocky foundation that has good soil stability and good road access already, but then the new location is going to be built in a bog with really unstable soil conditions that have to be stabilized, and if there's no roads in or out of the location and those are going to have to be built as well, then it wouldn't be a good cost estimate because you'd be using dissimilar conditions to extrapolate into the future and try and predict what the cost is likely to be. So what you have to keep in mind is that there's a lot more to the data than sometimes meets the eye, that you have to understand what were the economic conditions in the year in question where it was built, and most of those will be incorporated into the cost index, but some of the specific site values may not be. Does anybody have any questions before we move on to the learning curve material? Okay. So this is a picture of a factory. Some people might call it a sweatshop. The phrase sweatshop is kind of like a derogatory description of a place where people are working really hard, where the conditions are maybe unpleasant. You think of the working hours being long, and unfortunately that's the scenario for a lot of laborers outside of the United States, where they don't have the same kind of labor laws and where pay is a lot lower and conditions are difficult. So this is a picture where people are making clothing, and I don't know if you've ever seen video of people in a place like this, but they're just incredibly fast. Like they can sew a pair of pants in just seconds because they've done it so many times that they've really perfected the skill. They've found all of the shortcuts, and they've developed an economy of motion and a sophistication that you might not have on your first day. If you were sitting down in front of a sewing machine, you probably wouldn't be as fast at sewing a pair of pants as somebody who's been doing the same pattern and the same design for years and years. So we're going to look at a method for incorporating that. They call it a learning progress function or a learning curve. Just the notion that you get better at doing things the more times you've done it. we're going to look at a model that describes that improvement over time. And to use that model, we have to define a few terms. And one of the data points you need to apply this notion of learning curve or learning progress function is you have to measure how much time it took the very first time a function was done. So the first time you sewed a pair of pants, or the first time she sewed her shirt, then you assume that's the worst case scenario, because the next time you're going to have a little bit more experience and you will have become more confident at what you're doing, more fluid in the movements and so on. So K is the value that we use to assign the first time a task was done. And what we say is that they get progressively better from there, that subsequent tasks are completed at less than K. So, you know, a lot of industrial activities are starting to be replaced by automation. Some things are done by hand. Here you can see humans in chairs underneath Volkswagen cars, and they're putting things together, but it's becoming common to use robots as well for tasks. Like in the future, maybe the people take care of the robots, and so they're liberating us from some of the most exhausting and tedious tasks, but it is going to be an adjustment where people who previously were doing things are put out of work. So eventually, for example, they won't need a person to pull the things out of the shelves. Eventually, some robot or automation will come around that can pick the item off the shelf and put it into the bucket. And then eventually, someday down the line, they'll have a robot that can package the items in the bucket. And then eventually, they'll have an autonomous vehicle that can bring the items to your house without the need for the human. So it's always going to be really disruptive for what's happening with the people, but the point is that things are getting more efficient over time, whether it's people or whether it's machines. So back to this model for the learning progress function, for us to predict how long it's going to take to do something in the future, remember we have to know how much time did it take the first go around, and then we need a couple more data points beyond just that first time. We need to know how much improvement there was at a couple of additional points down the line. And in this model, S is defined as the ratio of time it took for you to double your experience. So doubling your experience means like when you went from the 5th time you did it until the 10th time you did it. So this person, let's say he's putting in an oil pan. If it took 40 seconds to install the oil pan on the 5th unit that he had installed, and then it only took 37 seconds on the 10th unit, when he went from the 5th to the 10th, that represents a doubling of his experience. And it only took 92% as much time when he did the 10th oil pan compared to the 5th oil pan. And so S is the ratio which represents how much faster you were when you doubled your experience at a certain task. And so this is what the curve looks like. You can see that it begins flattening out, that you don't keep improving forever, that this person, no matter how much experience he has, there are physical movements that have to be made, and he can't move his hands any faster than that maximum limit. So, picking up the oil pan off the ground, lifting it up, using the tool to install it, there's probably some theoretical threshold for what's the fastest possible that it could be done. And you can see how this learning curve approaches that value of the minimum amount of time taken to do a certain task. So here's the model. Z sub U is how much input resource units. So we usually think about that as time. So time in hours, time in minutes. How much time it takes to do the U is the output number that you're calculating it for. So if we wanted to know how long would it take him to do the 15th oil pan, then it would be Z sub U, U being 15. We would have to know K, which was how much time it took to do the first oil pan, and then U would again be 15, because that's the 15th one that we're trying to figure out. and then to the power of n, where n is the log of s, which in the previous slide, s was defined as the ratio associated with doubling your experience divided by the log of 2. So let me show you how that works. Let's say, for example, that it took you 85 minutes to sew a pair of pants the first time you tried it. And then the second time you sewed a pair of pants, it was 76.5. So already we've got a doubling of experience when you go from 1 to 2. So we could calculate S based on that. Going from 1 to 2, the S value is 76.5 divided by 85, and so S is 0.90 if we're looking at going from the first pair of pants to the second pair of pants. We also have data from the second to the fourth, and so that gives us a good opportunity to check the S value, because you know, the data is not always going to be perfectly smooth. It will in this example, but in the real world, if you had multiple data points, you could calculate the S associated with all of the data points you have and then average it. But in this case, going from the second to the fourth, then the ratio is 68.85 versus 76.5. And so once again, it's 0.90. So that defines S. Now what we want to know is how long will it take to sew the 10th pair of pants? So to predict how long it would take to sew the 10th pair of pants, we have to know the n value that applies. So remember, n here defined as the log of S, so the log of 0.9 divided by the log of 2. And so n for this is going to be negative 0.1520. And then once n is defined, we can substitute it into the formula. Let me show you. It's probably on the next slide if I remember. Yeah, here it is. So if we want to know how long it takes to sew the 10th pair of pants, then it's 85 minutes times u, which is 10, to the power of n, which is negative 0.152. So 59.9 minutes is how long it takes to sew the 10th pair of pants. And then if it asks for the total time to sew all 10 pairs of pants, we'd maybe want to automate that with Excel if we wanted to find out, for example, the first pair of pants, the second pair of pants, all the way through the 10th. Then we could put that model into Excel and automate the calculations. So let me just copy the formula over to Excel. So in this, we know that S, we had previously calculated as 0.9. And so if S is 0.9, then remember N is the log of S divided by the log of 2. Okay, so 0.152. Now, if we want to know for the first pair how much time it took, that was a given. So for pair number 1, we knew that it was 85 minutes. That was given in the details to begin with. And we want to know how much time was it for the second pair and the third pair and the fourth pair, all the way down through the 10th pair of pants. So let's see if this model accurately represents the values that we already know from the other given data. So equals K, here's K, it's the first pair of pants, multiplied by U to the N. So here's U to the power of N. I'll anchor the reference to the K value because that's always going to be 85 minutes. I'll anchor the reference to the N value because we always want that to be negative 0.152, but what's changing is the K that I'm on. So the second pair of pants, the third pair of pants, fourth pair of pants, and so far this is matching the data that we're given. We already knew the 76.5, we already knew 68.85, and so we could do all 10 pair of pants, and so then the total to do an order of 10 pants would be just the sum of all of these. So if we're going to do a cost estimate, we have to know how much labor to allocate to make 10 pairs of pants. It would be a poor estimate just to say, well, I'll have this person do the first pair of pants, and then how long it's going to take is 10 times that. It won't take that much time because they're going to get a little bit better at their task. So this function basically tells you how much better they're going to get over time, and then you could total up the entire order requirements for the whole sequence. All right. So I have an in-class exercise for you. Let me hand out those papers. It has to do with Rubik's Cube. Like if you're going to try and predict how long it would take you to complete a Rubik's Cube after you had 100 tries. I've given you some data here. And I think you should do these calculations, by the way, for the in-class exercise by hand. I don't think you should use Excel for this. I think it's better, more valuable to get the experience just by hand this first time. We've got a problem, though, with the data. They forgot to measure how long it took the first time they did it. And that's K. So I'm going to let you think for a minute about how to handle that. I think I give you a hint at the bottom of the page. But if you don't know K, but you do have some of the other data, think about how you'd handle a situation like that. So what we can start off with is defining S, because we have plenty of data points needed to define S. You can look at the second to the fourth, or the third to the sixth, or the fourth to the eighth. So any one of those could be used to define S. And all of them here, it turns out that S is 0.91. Once that's known, we can calculate N using the logarithmic functions. But the issue remains that we didn't measure the first time, like we forgot to calculate or run the stopwatch the first time we did the Rubik's Cube. And so what we can do is just assume that it followed the same pattern of being 91% of the time in the second try compared to the first try. So you can see what I'm doing is I'm back calculating K by just saying, if I use the 24 minutes that was required during the second try, and I say that the first try is going to be slower than that, I know that the ratio from the first to the second try is 0.91. So I can calculate the first try by dividing the second one by 0.91. Turns out to be 26.38 minutes. So then that's the K value. If we're trying to figure out how long it takes for the 100th try, U is 100, so then it would be 26.38 multiplied by U to the power of negative 0.1361. So it's about 14.1 minutes is how long we predict it's going to take, if the same pattern holds true through the entire. That's pretty far away from the data that we've gathered. So the trend may not continue indefinitely, but that's the best we've got for this model anyway.